Moving on now to our last big subject in operating systems, we'll talk about protection and synchronization. So what is protection in an operating system context? Protection is required for preventing errant or malicious misuse of the system by users or programs, ensuring that shared resources are used according to system policies, and to limit the damage caused by errant programs. So we want to really protect programs from each other and from, evil people who want to come and break in. So the basic means of protection that we already discussed is to provide each process, which is with its own separate address space. Only the kernel can access the full physical address space, and the process can only address the space defined in its process control block. So we saw that virtual memory and page tables help abstract away the physical memory from the program. But that also causes a problem. We have a problem with sharing data between processes, and if we actually do that and give two processes the same piece of shared memory, how can we maintain protection between them? So in other words, how do we enable inter-process communication, or IPC? So there are two models for this. The first one is what is known as the message passing model. In this case, we let the kernel handle it. So we have our memory space over here. We have two processes that get some sort of chunk of the memory, and we have the kernel down here, which may have some sort of structure or something inside it. And we can do this producer-consumer type of a model where we have send and receive operations, where the send can send some data and store it on some sort of queue in the kernel, and the receive can go through the kernel again and accept that type of data. But this suffers from a lot of overhead due to frequent system calls. Every time we want to pass a message between two processes or two threads or something like that, we have to actually go through the kernel, and that can be a little bit problematic. So the other option is what we call the shared memory model. In this case, we let several processes access the same memory space, where again, we have our whole type of memory space over here, but we designate some sort of piece of memory to be shared between these two processes. So we don't need any kernel intervention. Process A can go to and access the shared memory, and process B can access the shared memory. But how do we ensure protection on the shared memory? So can we use a queue to do that, as we saw before, that type of a buffer over there? And basically, in a producer-consumer model, we can really restrict the access. So only the producer can write to the queue. So we have, the producer over here and the consumer over here, and there's a straight line that only goes one way. And then, the producer can send something and, keep on doing this type of a loop, and the receiver can just receive something from that type of a queue. So for example, we could use a first in, first out buffer, a FIFO, and the FIFO has the tail pointer over here, which tells the producer where to write to, and it has the head pointer over here that tells the consumer where to read from, and that really enables us to pass messages between the producer and consumer where we don't have this problem that one of them is going to overwrite what the other does, or all kinds of other things that we'll be seeing soon that can corrupt each other's messages. And this works kind of well for two processes, but what happens if we need several producers or several consumers to access the same queue? And they need to share these FIFO pointers, and what can happen is they can really be accessing the same piece of memory at the same time. And there's really a problem here, because what happens if we want to both access the same memory? And for example, the first producer comes and writes his data to the tail, and then we have a context switch before he's able to increment the actual tail pointer, and then the second one will write over the data if we have the context switch. And so that's something that's really problematic. And we call this a critical section. So simultaneous access to a shared variable can really result in what we call a race condition. So I can give you an example over here of my wife over here and me, and we both happen to go to the bank at the same time, and we want to pull out money from the ATM. And we have $100 inside our account, and each of us decide to go and withdraw $50. So the procedure that the ATM works on can look like something like this. We have this withdraw type of an operation, that gets some sort of pointer or something to our account, and it says the amount of money we want to withdraw. And what we're going to do is we're going to first read the amount that we have inside our account, store it in some sort of local variable called balance. Then we're going to decrement the amount from the balance over here. We're going to write back the new balance and then spit out the cash from the ATM. So my wife gets there first, and she pushes the button, and she says that she wants to take $50 out of the account. And so we have this get balance, which goes and reads $100 from the account and decrements the $50 that she wants to pull out of it. But since we're having preemptive scheduling, what could happen now is that we could have a context switch all of a sudden at that point in her code. And then I hit my button and, I read the balance from the account and it's still at 100 because she hasn't yet written back the balance to the account. And so I decrement that 100 for the $50 that I want to pull out from the $100 in my current balance. And now my local variable of balance has $50 in it. I continue my operation and I put back this $50 amount into the account and the ATM spits out the cash. I walk away and I'm really happy. But now we have, I finished my process. I release, the processor and we context switch back to the other ATM. And now she puts the balance back. But remember, her local variable was at $50. So she put that back. And instead of saying 0 over here because we withdrew $100, it says 50. And we're really happy because we just made $50, but the bank went broke. So that is really a problem. And the code block where the shared variable is accessed, it's called the critical section. And what happened really was that we were accessing this shared variable, this balance over here, at the same time. And what happened is we context switched right in the middle of this access to the critical section. So let's see this in a famous kind of a gas station analogy. It's more like a bathroom analogy that you see in some sort of in some different types of lectures. So we have a gas station on the highway, and it has this nice bathroom over here with a little heart in the window. And two cars come and they make the pit stop. And the question is, who gets there first? And really, who gets there first? If these were two types of cars, of processes, would depend on the order that they arrived there. So the bathroom really is in the critical section of this type of a process. So let's see what the critical section problem is. The critical section problem is when we get a race condition. And it occurs in two cases where the several processes or threads manipulate a shared resource at the same time. So really it has to deal with a shared resource. And the outcome depends on the particular order in which the access takes place. So if these two conditions exist, this is the critical section problem. Okay, so what we need to do is we need to have synchronization around the critical section. We need to make sure that no race conditions can occur. And how do we have this? We have some sort of, let's say we have this infinite loop type of a thing, and we have our critical section over here. What we have to do is surround this by some sort of entry section and some sort of exit section that synchronize between the two and prevent any type of race condition happening within the critical section. So how do we solve critical section problems? And the main thing is to enable mutual exclusion. Mutual exclusion means that at most one thread or process can be inside the critical section at a given time. So as long as only one thread is in its critical section, we have mutual exclusion. We're only accessing the shared variable by one process at any given time. That's not enough. We also have to ensure progress, which means that a thread outside its own critical section cannot prevent another thread from entering the critical section, or else we can have something like deadlock or live lock. And another thing is bounded waiting, where a thread that wants to enter its critical section will eventually be allowed to enter it. So we're going to mainly discuss mutual exclusion over here, but progress and bounded waiting are two other important points in operating systems that we need to make sure when there is synchronization between two processes. So what is mutual exclusion, or a mutex? A mutex is a primitive that enables synchronized access to a shared resource. So it's some sort of variable that's shared between us, and we need to enable synchronized access. And what we're going to do is use a mutex. So how can we do this? We can define something like a lock. A lock is just some sort of a variable or whatever that has two operations associated with it. One would be called acquire, which means I acquire the lock. I have the rights to enter the critical section. And release would mean I finished doing whatever I was doing and I can give up the rights to be in the critical section. We can often access a lock with what we call a spin lock, which means we're going to busy wait on the lock until it's free. So we have the lock over here. It has some sort of a parameter if it's held or not, and we define this acquire that we spin lock. We look at the lock, and as long as it's held, if the lock is 1, right, then we're just going to keep on spinning over here on this this type of a while loop. Once the lock is released, and it equals to 0, then we can go and we can acquire it by sticking a 1 over there. And how do we release the lock? We're just going to put a 0 on it. We have the lock if we're running a lock release. So that's called a spin lock, or just busy waiting onto the lock until it's free. So the problem is that that spin locks have critical sections too. So what happens if we context switch right over here? What we did here is we read the shared variable. So we looked and saw what the lock value was over here, and on the next operation we went and we wrote the 1 to it when we saw that it was free. What if a couple of processes or a couple of threads were spin locking on this line over here, and once they both saw that the lock was free, who actually got to write the 1? That's a critical section over here. And so we cannot have a context switch happen in between these two lines of code. So that means that the acquire and release operations, they must be atomic, which means that they're executed without interruption. And to enable that, we'll need help from the hardware. We can have atomic instructions such as a test and set instruction, which you can see over here, or to disable interrupts to prevent context switches. So a text and set type of instruction will look at the lock, and if it's free, it will write a 1 to it. And that we want to have as something that is going to be an atomic instruction, which we'll discuss more in a few seconds. So let's go back to our gas station analogy, and now we will have a mutex to protect our critical section. So the gas station has one bathroom, and now we added a key to the bathroom. So the first customer comes, and she's the first one there, so she can acquire the key, and she's very happy, as you can see. But another guy comes, and poor guy, he needs to wait until this lady relinquishes the key, and then he can go acquire the key and use the shared resource. So let's go back to our ATM example now using a mutual exclusion. And again, here me and the wife are. And remember that this is our critical section over here where we're actually going and accessing this account variable, which is shared between the two of us. And what we're going to do is we're going to add that entry and exit area, but with an acquire and a release of the lock on this shared variable, which is the account. So what's going to happen is my wife got there first, so she's going to hit this acquire, and she's going to acquire the lock because it was free. So she holds the lock over here now. And so she can continue her operation. She, again, does this, get balance. She sees it's $100. She removes the amount from it. Now that's $50. And I come in, and I want to come and have a context switch, and somebody thinks that I'm more important, so they want to give it to me. So what I do is I hit this acquire lock, and wait a second, I see that the lock isn't free, so I have to busy wait on this lock over here. So I have to stop, and she gets to continue operating. So now she's going to go and write this $50 back into the account and update the balance, and then she's going to be able to release the lock because she went out of her critical section. She didn't finish her operation. She just finished working in the critical section over here. I see that the lock is free, and now I acquire the lock because I've been busy waiting on it. So I can come here and context switch, and so I get the balance, and now I see the balance is $50. I remove the $50 from it, and I write back 0 into the account, and now I can release the lock. There was no reason to context switch, so I can continue, spit out my cash. I got my $50. Now I context switch back, and my wife can get her $50, and we can all go home. The bank is happy because I don't have any money left in my account. So how do we implement synchronization? Well, it's really a black hole, and it should not be approached by the faint-hearted. Synchronization really can cause problems. It becomes very, 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 very confusing very quickly, and many software programmers have fallen deep into this black hole. And that's why usually we have synchronization libraries that are really carefully written according to the specific hardware and the different types of operations that it supplies in order to ensure that really you can easily program mutual exclusion and race-free code. So really that's a black hole, and there are specialists who really deal with writing these synchronization libraries and making sure, improving that they really work all the time under every type of condition. So you can do this through software only. It usually still requires additional types of primitives such as hardware barriers, which I'm not going to be discussing over here once you're using multiprocessors. So for example, Leslie Lamport introduced Lamport's bakery algorithm in 1974, and there are several other algorithms like this, but they really require many processor cycles to implement this type of mutual exclusion. So it can take, dozens or hundreds even of cycles just to acquire or release a lock. And I just wanted to mention here that this Leslie Lamport, we can thank him for being the law and the LaTeX, type of thing. He's the guy who wrote it. Okay, so locks are usually implemented using atomic operations instead of using these software-only approaches. So these are, what is an atomic operation? As I said before, it's a sequence that guarantees to complete within a single indivisible operation. So it's something that we know that there will not be any type of context switch or something like that that happens in the middle. And when we learn some sort of operating system class, they just assume that there are these instructions in the processor, but we're hardware guys, and how do we actually implement these types of things? And let me tell you, it's not that simple, and it took me a while to figure this one out. So what are these atomic instructions? Well, there are three main types of atomic instructions that you can usually find inside synchronization libraries. And this is a generalization of categories. They have different little intricacies between them, but there are three main kind of categories of these things. The first one, which was very popular before we had multiprocessors, was called atomic exchange. And that means we want to swap the content of a register and a memory location. Why does that help us? Well, we have some sort of an operation like this, where we have this atomic exchange over here that keeps on exchanging the content of some register R1 with the memory location that is inside lock over here. So why does it help us that we keep on exchanging or swapping these two things? Well, we have this, this spin when R1 equals 1, and we initialize R1 to 1. So what we're going to do is, let's say the lock was taken, so lock equals 1. We're going to go into this loop, R1 initially equals 1, and then we're going to exchange R1, which is 1, to the lock. The lock, which was 1, is going to come back to R1. So R1 equals 1 at the end of this, and that means we're going to continue in this while. So as long as the lock was taken, we're going to be stuck inside this loop. Once the lock was released by somebody else, lock is going to be equal to 0, and then R1 is going to be equal to 0. R1 is, which was 1, is going to be written into the lock. That means the lock is now 1, but R1 equals 0. That means we're going to exit this loop, and we hold the lock. We can continue doing whatever we want. We acquired the lock with this. So if the lock was free, it returns 0. Otherwise, we spin on this loop over here. Okay. But however, the problem with that is it means we continually write to memory. As you saw, this exchange operation keeps on writing a 1 into this memory area. Every time we spin over here, we write a 1. And that's something that's really bad for places where we have several processors that have different caches. We keep invalidating the cache of other people who are waiting on this lock. And that means that we're really wasting a lot of power. We're blocking up the interconnect by having all these cache misses and invalidations and moving around the cache block all the time. This is something that's really bad. I didn't go into cache coherence protocols and so forth in this course, but it really turns out to be something that we don't want to do. We don't want to continually write to the cache from different processes. So instead, we can use a test and set type of a command, which is what I just briefly showed before. So in a test and set type of a command, we first read the lock, and if it's free, then we acquire it. So the semantics of such an operation, such an instruction, would look something like this. If the lock is free, then we lock it and we reset this R1 so it will escape this loop over here we had. Otherwise, we keep R1 at 1 and then we keep on spinning inside the test and set. So the thing is that we don't need to write to memory while spinning because we first read the lock and we only actually go in and write to the lock if the lock is initially free. But since this is atomic, we still are able to acquire it during this one operation. So we don't need to write to memory while spinning, and that's much better than an atomic swap. Okay, but it still requires a load and a store within a single instruction. So we're reading the lock equals 0, and then we're writing lock equals 1. That means we needed to access the variable that's inside memory twice in the same instruction. And as we've learned about in our different types of pipelines, we can only do one load or store within a single instruction. If we want to do two of them, we'd want to first read and then decide and maybe change something on the variable and then write to it in a single instruction. We'd have to make make a deeper pipeline with extra memory access pipe stages, and that would be something that would really give us a performance hit, and it's not good for small simple processors. So the third option is what we call a load link store conditional operation, and there we're going to split the operation into two commands. It's going to simplify memory access. It's also going to divide the kind of operation into two parts where we can stick other code in the middle. And let's see how this one works. So load linked and store conditional is an approach that creates an atomic operation with two instructions. So it's an atomic operation. It's not an atomic instruction. We have two instructions that are each atomic, and together they're going to make one full atomic operation. So what is it? Load linked, also called load reserved or load locked, that we just carry out a regular load from memory to a register. And then we do something which is called to create a reservation on the load. Okay. And then we have this store conditional, which is the other command. And what store conditional does, it attempts to store a value to the memory location. But if the reservation was broken, the store fails. So seeing this, how can we implement a lock with this LLLR type of a thing? So we have this kind of a loop that's going to keep on going, spinning on this thing. So what it's going to do, it's going to load, 1 into our 1 register, and then it's going to perform this load linked into R2. So what it's going to do, it's going to go over to this lock variable, which is somewhere in memory, and it's going to load it into R2. But while it locks it, it also provides a reservation on this address. So then if the lock variable was non-zero, what it's going to do, it's just going to spin back, because as long as it wasn't 0, it's going to keep on trying to see when the lock actually is released. Once it was 0, it falls through, and then it applies this store conditional. It wants to write 1 into the lock variable. And so this store conditional will either write a 1 into the lock variable, which means that I actually acquired the lock, or it will fail. And if it fails, it's going to return a 0 over here, and then we're going to have a branch equal. So we're going to, again, go and spin on this thing. So store conditional will fail if we did not still have the reservation. So the question is, what breaks a reservation? And you can see kind of a technophobe type of a comic over here about reservations at restaurants. So it's not exactly the same thing, but breaking a reservation can happen in many different cases. But in general, when we have a context switch in the middle of our procedure over here, then we're going to break the reservation, because that means we're not atomic anymore if there was a context switch in the middle over here. And the other thing that can really break a reservation, if we store to the reserved address, which will happen by another processor, because we're really inside the same process that's running over here. But if another processor stores to the reserved address because it's running in parallel, then it's going to break the reservation as well. So the reservation is kind of held in a hidden register usually. It's not something that's shown to the programmer. It's something internal to the processor. But since it's a register, it can be accessed in parallel to the memory access. So we can apply reads and writes while we're also accessing memory. It costs us just a single type of a pipe stage. It's not a big deal. It's really simple to do on even like one of our 4 or 5 stage pipelines that we have in our simple RISC machines. And how to actually implement this reservation is something that is not necessarily defined. It can be kind of flexible. So how is this done in RISC-V? And RISC-V does adopt this load link store conditional approach, though they call it load reserved. So a load reserve, it is an operation like this. What it does is it loads the memory content that is at RS1, so this indirect type of addressing, into RD. So it's going to just do like a regular load over here. The .w is for words, so that's for 32 bits. They have a .d for 64-bit processors. So we're going to just load this word into RD. So that's basically loading the lock value into this RD register. Then the store conditional is going to actually go to, again, some sort of indirect memory. It's going to store R2 into this memory. And what it's going to return is, if there is a success, it's going to return a 0. And if it's going to be fail, it's going to return a 1. So that's kind of opposite of the semantics I showed on the previous slide, but it's the same type of thing, just inverted. So that's the store conditional. And so what it's going to do, it's going to release the reservation in any case, and it's going to return 0 if this was successful. So there are some further constraints that are documented in the spec. For instance, we have to limit the number of operations we can apply between a load reserved and the store conditional, and we can have to limit the type of instruction. So you're not allowed to branch out there or perform other loads or stores in between, and there have to be up to about 16 instructions, and this will help with those types of progress and bounded waiting and so forth that we discussed before. RISC-V also supports additional atomic instructions such as atomic swap, atomic add, atomic XOR, all kinds of things like that. There's a list of them. But if we have a simple processor, they can just be implemented as a macro with the load reserved and store conditional command. So for example, we can implement an atomic swap with just load reserved and store conditional commands, as you can see over here. So it's pretty simple to do. So just as a side note, there's another approach to acquiring mutual exclusion, which is by disabling interrupts. So disabling interrupts is a simple solution for mutual exclusion by ensuring that there are no context switches while accessing the critical section. And as Garfield says, just don't interrupt me. The problem with disabling the interrupts is that it's only available to the kernel. You can't allow the user level to disable all the interrupts in the machine. It's insufficient on a multiprocessor because each processor will have its own interrupt mechanism, so this probably won't work. And long periods with interrupts disabled can really wreak havoc on all kinds of devices that are connected in some sort of a system. So you should really use disabling of interrupts to build higher level synchronization constructs, such as a lock. So acquiring a lock can be just to clear the interrupts, and releasing the lock can be setting the interrupts back. And to finish this discussion of synchronization, I wanted to discuss semaphores. There are other types of synchronization primitives that they have in operating systems. I'm not going to go into them, but I'm sure that you've heard of semaphores before. At least you heard the word, and you've really been waiting for me to explain what they are. So I want to have 3 laws of semaphores. And my first law of semaphore is that the only thing that anyone ever remembers from their undergrad operating system class is that they learned about semaphores. Everyone remembers the word semaphores. Everyone remembers it because they have no idea what a semaphore is. So my second law of semaphore is that no one actually remembers what they are. And what is this word semaphore? So I looked it up, and it's basically a type of a signaling that is used in ships and trains and all kinds of things where you can take flags and write different types of words. So here is the word semaphore written with flags that are doing semaphores, signaling to others. So a semaphore is a signal type of a thing, or it's like an alphabet out of a signal. But nobody actually remembers what a semaphore is. And the third law of semaphores is that the only thing that anyone actually remembers about the semaphores is that this guy Dijkstra over here, who made the Dijkstra algorithm and stuff, he's the guy who invented them, and that there are these variables P and V that they come from Dutch because Dijkstra was Dutch. So that's really my 3 laws of semaphores. No one has any clue about semaphores, and it took me really a long time to kind of understand what they are. I'm still not sure that I have a complete hold over them. So what exactly is a semaphore? That was the question we really wanted to know. And basically, it's a shared non-negative integer. So it's just a variable that can have values like 0, 1, 2, and stuff. Yeah, that's all it is. The big deal about this semaphore is it's just an integer. Okay, so what's the big fuss? Why is it different from any other variable? Well, there are 2 operations that can be applied to it. One of them is called wait, and one of them is called signal. So wait means that we're going to block, we're going to spin lock, busy wait, until the semaphore variable is larger than 0. And then once it's larger than 0, we're going to subtract 1 from it and proceed. The signal operation is just going to increment it. So this is the big deal. And both of these operations, wait and signal, they must be atomic. Now, just a side note, I said something about Dutch. Well, often wait and signal are called P and V, which causes even more confusion because P and V come from Dutch. P is for proberen, which means to test or try, and V is for verhagen, which means to increase. And actually, those are not the original things that Dijkstra used, but that's kind of what they're considered now to give some sort of meaning in Dutch. So if people use P and V, just tell them use wait and signal. It makes a lot more sense. So again, wait is going to just block. I'm going to wait until I see that the semaphore is non-zero, and once I see the semaphore is non-zero, once I see the semaphore is non-zero, I'm going to subtract 1 from it. And signal is to say, listen, increment the semaphore to be higher than 1. And that's a way to signal between different processes. So how does that exactly help us? Well, as I said, it allows one thread to signal to another. And this is a good thing because unlike acquiring a lock, signaling is non-blocking. And that can be really useful in all types of process synchronization. So let's see what that means. So let's see some examples of how semaphores can be used. And there are many different types of things that can be done, but they're hard to get your head around. And people give bad examples all the time, which cause confusion, which I'll discuss in a minute. So one example is using semaphores for precedence between processes. So say we have two processes, A and B. And process A has these operations, A1, A2, A3, A4, A5. And process B has 5 operations as well, B1, B2, B3, B4, B5. And these processes are sequential with, these operations are sequential within process A, and these are sequential within process B, but we have no, nothing that's kind of deciding which one happens before the other. And let's say it's very important for us that A4 actually is completed before we go and we do B3. So that can happen in many different cases. So we can use a semaphore to solve this problem. So let's initialize a semaphore with the 0, and then we'll stick a wait on this semaphore here after B2, and we'll stick a signal on the semaphore after A4. So what's going to happen, let's say that these happen in parallel. So A1 and A2 happen, and B1 and B2 happen. Well, B2 reaches the wait operation, and it sees that the semaphore is equal to 0. So it's just going to spin on this operation here, and it's not going to continue to B3. Process A, in the meantime, is going to continue. It's going to do A3 and then A4, and then it gets this signal operation, which is just going to take S and increment it to 1. Once it increments it to 1, this busy waiting over here sees that S is larger than 0. It's going to decrement it and continue. Another example could be showing how to use a bounded buffer. So that type of a FIFO type of thing we saw before. And it's bounded. It has a limited number of things inside it. So we can use semaphores to signal to between the two processes when there is something inside the buffer or not. So we have some sort of shared memory that has a buffer with, n items inside it, and it has some integers called in and out. And there is a semaphore that's shared between them that is called chars. So the producer in this case is just going to have a simple thing where it's a send operation where it's going to put some sort of new character inside the buffer, increment the tail pointer over here, and then increase the semaphore by 1 by signaling to it. So every time he puts an item in, the semaphore is going to grow. The consumer, on the other hand, is going to have this receive operation where what it's going to do, it's going to wait until there is something inside the buffer. In other words, the chars is larger than 0. If chars is equal to 0 as it started, that means that the producer hasn't put anything inside. And once it's larger than 0, it's going to go and it's going to read that character out of it, and it's going to return that. And remember, when chars becomes larger than 0, it's going to decrement it by 1 and then continue. And then again, probably spin on this, continually loop on this. But note that this little piece of code over here is insufficient for multiple producers and consumers. In order to do that, you really need to have mutual exclusion, and mutual exclusion is not a semaphore. So that's what I want to really get straight with you. Semaphores are not mutexes, okay? A mutex is a lock that can be used for mutual exclusion to protect a critical section. Let's give it its name. It's a mutex. It's not a semaphore. A semaphore, remember the flags? That's why it's called a semaphore. It's used to signal a process. It's for signaling. But everyone is so confused. When you ask somebody what is a semaphore, they explain to you what a mutex is. A semaphore is not a mutex. Why is everyone so confused? And there is so much confusion about it. And I would say that someone somewhere decided to confuse everyone by calling a mutex a binary semaphore. And that's really because you can implement a mutex with a semaphore. So if you have a semaphore that can only be 0 or 1, it can be used as a mutex. But that's not what a semaphore is. Remember, a semaphore, it really can be something that is 0, 1, 2, 3, etc. It's a non-negative integer. They often call that a counting semaphore, but that's just a semaphore. It's not a counting semaphore. So the harder thing about that is that certain systems like free RTOS, they only provide semaphores. So a mutex is just a type of a semaphore where they use a binary semaphore to implement mutexes. And this really all causes a lot of confusion because people don't explain semaphores correctly. Then they don't explain how to use them correctly. And then everybody thinks that a semaphore is just a mutex, which is kind of easier to get around in our head. So to help you remember, let's see what happens if we use semaphores as mutual exclusion in our tactically situated gas station that everybody stops at to use the loo. So let's have our analogy about semaphores over here. And now we have this bathroom, this great gas station. It has 2 bathrooms and it has 2 keys, but the 2 keys are really the same for each of them. So the first customer comes and she acquires a key. She decides to go into this top bathroom. And the second customer comes along and he acquires a key and he decides to go into the bottom bathroom. But then our poor third customer, who always seems to be arriving late, he arrives and the semaphore is at 0. There is no key that's available. But luckily for him, this guy finishes and he can go and acquire, the key that was the semaphore grew to 1 and he didn't have to wait anymore. But now, which bathroom does he choose? And what happens if he chooses the wrong bathroom? Nothing is protecting him from going to the same bathroom that this poor lady, who just became really embarrassed, was already inside. So semaphores should not be used for mutual exclusion. You should use semaphores for signaling, which is what they're all about.